thanks so much to everyone for joining us for today's Concrete Sustainability Hub webinar. My name is Jeremy Gregory, and I'm the Executive Director of the Concrete Sustainability Hub. And we have these webinars approximately on a monthly basis to tell you about some of the activities that are going on in the Concrete Sustainability Hub. Today we have the pleasure of having Professor Franz Olm, who's the Faculty Director of the Concrete Sustainability Hub. And he's going to be talking about a topic that spans a variety of different areas in which we have research in the Concrete Sustainability Hub about buildings and cities and resilience and energy. So it's a good topic to kind of present everything or a sample of everything that we're doing. Just as a reminder, we have everyone on mute because the number of people that there are, and we will have a Q&A at the end. There's a button in the upper right of your screen that says Q&A. So please, we encourage you to type in questions there, and at the end, I'll be asking whatever is typed in there for Franz to answer. So with that, I'll turn it over to Franz. Please take it away. Franz, I think you might be on mute.
Yeah, thank you very much, everybody.
Go.
Yeah, thank you very much, Jeremy, and welcome to everybody close and far to take time out of your busy schedule to listen to and discuss with us the concept of resilience, urban physics, and engineering. So the question which I want to address here is a question of resilience, but let me start out here with the question which was raised in the invitation about cities. Is a city, and here New York City, for instance, is New York a liquid or a crystal? And I don't mean this in a sense of a budget. That's actually a typical question which a scientist or physicist would ask. As engineers, we have to, or business people, we have to ask the question, well, if New York or LA or whatever type of city was a crystal or solid or liquid, does it really matter? And what you see here is an image of the aftermath of the Hurricane Sandy in New York, of a whole block being destroyed due to Hurricane Sandy. So this is what I want to address with you today, to show you some of the results which we obtained trying to develop a quantitative engineering, sustainability, and resilience approach for cities, buildings, and infrastructure. Now, I will start out with a motivation, first of all, talking about what is sort of the point which we want to address and what we don't want to address. Then I will talk a little bit about how we analyze cities using approaches which come from statistical physics, and then address the question engineers need to address: why does it matter? I will address urban heat island effects. I will speak about the next storm and resilience of buildings and communities before concluding. So if chemistry and physics was the answer, and that's what you're in for today, one can ask the question, what's the chemistry of a city? And people have looked at this problem from the following perspective. What you see here in this graph is, in the beautiful log scale, the city population over city population average for a huge number of cities, actually 360 US cities here. And on the y-axis, also in a log scale, crime, GDP, income, and patents. And people have made the case that the more people live together, so the denser a city is, well, the power here is greater than one, meaning crime, GDP, income, and patent increases with the density. That's not a topic which we want to address because, as you readily understand, crime, GDP, income, patents are value propositions actually associated with social and political developments. What we want to address here is something: how can we be quantitative with regard to resilience of cities at city scale? Well, another quantity which already is a little bit more engineering-like is when it comes to infrastructure. What this graph shows us from the same group here of Bettencourt and others, is the road area in cities as a function of log population. And what you show here is that the density of people actually is the effect of economy of scale, meaning that the more people live together, the less roads you have. But please note clearly that this doesn't tell us anything about the operation of a city. Just remind yourself of your commute this morning, of the traffic jams you have to overcome. So the density per se is not a quantity which is relevant to describe operation and so sustainability of a city, and as we're going to see, even when it comes to resilience of cities. Another one which is very dear to me is about the worldwide material consumption, and that's some of the motivation of the Concrete Sustainability Hub, the fact that the worldwide cement production, which you see here, increases substantially. You see in 2008, the recession in 2008 was just a blip in this development, and you see this increase which bypasses largely the world population, which makes cement and thus concrete one of the most materials consumed on planet Earth. Roughly 2 cubic yards of concrete are consumed annually per capita on planet Earth. Again, what's the challenge here actually? By 2050, 67% of the world population, 82% in the United States, will live in urban environments. Classically, city planners have used density as an equilibrium parameter, meaning describing at a certain stage certain developments, whether this is income patterns, hospital distributions, with regard to a density of people. But it is very difficult actually to use that parameter to address sustainability and resilience of cities. And just to make my point about this here, what I would like to show you here is an effect of urban heat island effect. What this graph here shows us is the temperature difference between inside and outside of the city, which is the urban heat island, as a function of density of buildings. And even though you may convince yourself that there's an increase with density, clearly this spread of data here of all these cities does not allow us to be quantitative and link density directly to the temperature difference and address, therefore, questions like air pollution, water quality, energy demand, and elderly mortality. So density alone is not sufficient. So to motivate our approach, let me tell you what was sort of the last big findings on the material side and bring this, the way how we do research on the material side into the realm of cities complexity, sustainability, and resilience. So what you see on the left side is the 2009 first molecular model of calcium silica hydrates, which is the binding phase of concrete, and which makes concrete such a sustainable material. The most recent progress there actually was attained with a technique which structural engineers are very much familiar with, which is the problem of statically determined or statically indeterminate structure. As you know, if you have a structure where you have as much unknowns, so for instance here for the Eiffel Tower, the number of truss elements which are in the system, when you have as much elements as equations to solve the problem, we call this a statically determined or isostatic system. When you have too little, that's not what you want to have in a structure, because then the structure is floppy, it's moving. Obviously, that's what you don't want to have when you walk over a bridge. It would be moving, so you don't want that here. And then there's the other extreme, which is very often used in structural mechanics, statically indeterminate structure, where you have more constraint than equations to solve the problem. That type of technique, which is well known from structural mechanics since 280 years at least, is applied to molecular structures. And in fact, if you do this, then you actually realize that here the number of constraints here, and you look at the key parameter of cementitious materials, which is the so-called calcium to silica ratio here, actually has a very interesting behavior in terms of this number of constraints. So if you look at this here, then you find out that today's concrete actually have a number of constraints which make them rather floppy, the classical concretes here, which explains that there is some margin to develop on the material side to obtain improved materials with higher resistance. On the other hand, when you go to over-constraints or rigid systems, they are typically crystal systems here, and these are materials which are used in high-performance concrete or ultra-high-performance materials where they're crystal structures. And in between, there exists here one type of material around a calcium of silica ratio of 1.5, where the system is isostatic. Now, why does this calcium matter, actually? Because it's all about the environmental footprint of concrete. In order to produce concrete, one has to take limestone, CaCO3, decompose it in lime, and CO2 is released in this process. And that's one of the sources of the environmental footprint of concrete. So because of the huge amount of concrete which is produced worldwide, this amounts to quite a bit of CO2 release in the world. Having said this, if you take this per unit strength or per unit mass, concrete is a very efficient material, but the sheer mass of concrete consumed worldwide to meet our needs of shelter, housing, schools, infrastructure warrants to look into improving concrete at this molecular scale. If you want it this way, today's concrete at an atomic scale are basically on short distances glass-like, amorphous, here these scales here, and mineral-like at larger scale where they're ordered. So similar like this structure here on the right-hand side, which is glass, of course, glassy on short distances, but then you have a repetitive motif which is crystal-like. So why does that matter if you look at strength properties, for instance? If we are able to increase the properties, fracture resistance, and longevity of concrete material, we can do actually more with less material. And here what you see is in effect results from our work, which shows actually that if we were to lower our current calcium to silica ratio to lower values, 1.5, we would be able actually to increase the intrinsic fracture resistance of the material by at least 80 to 85%. So which means we could do more with less material. The same thing is shown here on the right side. This is the creep behavior, so the time-dependent deformation. The creep modulus, the inverse of it, defines the creep rate. So the higher the value, the slower the material creeps. We find there a similar type of concept that as we move towards the isostatic, statically determined molecular structures, we would be able to improve the durability of the material. So you see that these concepts, which come from basically implementation of concepts at the molecular scale, provide a wealth of information to improve the durability and the sustainability of concrete materials. So why do I bring this up? In order to translate actually molecular complexity, which takes place at scales 10⁻⁹ meters, to city complexity. Well, you will immediately understand this if you realize that people in physics look to identify glass-type structures or crystal-type structures by means of this so-called pair distribution function here. What is that actually? Imagine you have a certain atom in a structure, and you make circles around this atom and ask yourself, how many atoms of the same type will I find in a certain distance? And you do this for all the same type, for all atoms in the structure. Well, that's the way how you identify actually in molecular science whether a structure is glassy or crystal. Well, what we do in essence is exactly the same thing at city scale, where we take all the building stock of a city, and atomize them in the sense that we take each building at its center of gravity here and look how many buildings are around it. So what does that mean actually here? It means we are looking here at the local density of the buildings divided by the average density of building, which is the quantity which city planners typically use in the system. You not do this only for one building, but you do this for all buildings in a city stock. And just to make the point that this analogy is not just an invention, just a thought experiment, it's sufficient to look at some city plans. So if you take here Los Angeles here at the scale of tens of kilometers, and you compare this here with a glass-like structure obtained by SEM imaging of a material, you see that this disordered structure of LA is very much akin to what we see under SEM scanning electron microscope at tens of nanometers. Or if you take Chicago, which is a very regular grid-type city, and you compare this to crystal-type structures here, where you have clear grain boundaries, you see the analogy actually between the two things here to describe the geometry of a city. Now, to make the point then quantitative, if I now take this pair distribution function, so I've done this for all the cities, and you compare, for instance, a liquid argon here. At the x-axis, we have the distance normalized by angstrom, the elementary molecular distance here. And you compare this to the city of Seattle, you actually see that a liquid argon, which has this very characteristic structure here, is very much akin to the pair distribution function of the building stock of Seattle. Similar, if you do this for crystal argon, you see these very pronounced peaks here, which come from the fact of a very ordered structure, highly ordered structure here, which is very much akin here to Chicago here, when we normalize the distance between buildings by the average building size of the system. So you see here a signature of the city applying molecular science tools to the scale of the city. To be quantitative here, if you take here Chicago, you see here this very clear peaks here now in real distances here, or here Boston, so you see Chicago is a crystal, Boston is more liquidish, gas-like here. The interesting thing about this function is also that the integral, basically the surface here in yellow, here gives you an information about the average number of neighbors in your first surrounding, in the first shell around the buildings. By neighbors, I mean the number of buildings in your vicinity. So this information actually provides a refined geometric description of a city in terms of information about its texture on the one side, without going down to the teeny weeny little details which a city which characterizes the next corner of an individual building. So what we are covering here is basically the scale between the average scale of building density and the refined scale of wind of a major avenue in a city. So the question which I raised, or the scientists raised, which is New York a liquid or a crystal? So, of course, New York is more than just Manhattan. If you look at Staten Island, you get a signature, very characteristic signature here. On the other hand, Queens here has a signature which is also quite similar. So is it a liquid or a crystal? It's neither. Actually, it's a glass, but it has a long-term amorphous system. So that would be the analysis from a physicist. But the question which we need to address is, why does this matter? And I want to show this through 3 examples. The first one is urban heat island effects and energy management of cities. How, given a certain information about the texture of a city, can a city actually manage its energy consumption because of this structure? So the first point to be noted here, if you take here this temperature difference between inside and outside of the city, and you plot this as function of a parameter which involves the first shell distance, the characteristic building size, and the numbers of neighbors determined from this pair distribution function here, from this integral of this first curve, you obtain here, you see that these values of all these cities, which are not only US cities, but there's also some European cities, or still European cities like London, but we have also Paris here. You see they all follow a specific characteristic pattern, which means that disorder actually matters when it comes to this urban heat island effect, this difference in temperature between inside and outside of the city. In fact, why does this matter? If you look at an energy consumption of a city and you go down to the scale of your gas bill, the gas bill which you receive for your home, a very interesting pattern actually emerges. What I show you here is actually analysis of data for 6,000 buildings in Cambridge, Massachusetts, our hometown here, the gas bills, where we determine the gas consumption from the gas bill per month, and we divide this here by the surface of the envelope. Now, what you realize actually here is then, for Cambridge, Massachusetts, for instance, heating and plotted versus the monthly average temperature at Logan Airport. So what you see then here is that there is a tendency that beyond a certain, below a certain temperature, which is on the order of 16 to 14, 13 degrees, outside temperature, not comfort temperature, outside temperature, heating systems kick in, and that's a very characteristic curve. Note also that the inverse of this slope here, or that this slope actually is the inverse of an R value, the resistance which defines the quality and effective R value of the entire building. And what you can do then here is, of course, you can then use these values from gas bills in order to identify which buildings a city should redo in order to gain the highest reduction of energy savings. So, for instance, what I show you here is the percentage of retrofitted buildings here. This is the normalized energy savings just identified here, given a certain R values determined from the gas bills. You can see that if Cambridge were to redo only 10%, but very specific buildings here, it could reduce its environmental impact by 30%, so energy consumption at the city scale. So here you see how big data can, through modeling, plays a role to inform decision makers at city scale how to improve the energy consumption of the city scale. But how are these two phenomena linked? On the one side, the quality of the building stock and the need for the city to do works on the building stock, and on the other side, this delta T, this temperature between inside and outside of the city. In fact, if you look at this here, once we have this information about the first shell neighbors, we can develop a very simple engineering model. Just take a pipe model with buildings, number of buildings defined by Cn, by the information coming from the pair distribution function. And then consider that there's a certain outflux of energy from these buildings. What you then see, what is the increase of the temperature in the first shell compared to the outside here, follows here a very characteristic line. Please note that line is only valid between here and there because that's the overlap area. And you see that this fits actually perfectly. This simple engineering model fits extremely well the urban heat island temperatures between inside and the outside of the city. So this provides a means for a city then to take action, either at the envelope scale, that's one way of doing it, at city scale by change the numbers of neighbors, that could be a decision. One could build either denser or looser, so there is a decision to be made. And at building scale, the characteristic building size at building scale. So city manager actually with this type of approach, using on the one side the texture information from the city with the building stock gas bills, are able then to make rational decision based how to reduce the environmental footprint of a city related to energy consumption. Let me take a second example here. How do cities actually react then here when you have a hurricane or a storm coming in there? So the question here actually raised is, does it matter the way how we build, ordered or disordered a structure? So these are all quite ordered structure here. So question, does city texture matter actually in the way how cities respond to storms, smog, etc.? Well, the way how we do this is, once we have the city information, we can create synthetic cities, by which I mean we can create cities which reproduce the statistical information which we obtain by the city texture. So we can create ordered cities, disordered cities, wide streets, narrow streets, etc. Information which comes from the texture of the city, and these are just graphs of the city. And just to show you this here, how this works, so if you have a storm coming from the outside, you see that an ordered city amplifies the temperature, the outside temperature, much more than a disordered city. So the question which is then raised is, how does that affect the pressure which acts on the building and the likelihood that water will stay inside the city or will be trapped inside? Now, let me have a look on this here from a perspective of the pressure, because the pressure on the buildings is an important question which is raised, which is required for structural engineers to design the buildings. What turns out actually, if you look at the inlet velocity over the range of pressure, so min-max pressures here, you actually find out that this is sort of almost follows the classical Bernoulli flow equations. I will not enter in that here, where gamma here is an order parameter which depends actually on the order of the city. So gamma is an ordered, 10 is an ordered city, gamma equals 4 is a disordered city. And you see that the pressure actually, which should be considered of a city actually, depends on the texture. This is an amplification value compared to the value which is today in the design codes. Then you may ask your question, was Hurricane Andrew, given this regular layout, was this only a question of the city properties, or did the ordered structure here play a role? We wanted to be a little bit more quantitative and bring it back to last year's hurricane season, 2017, looking at damage in Florida, specifically Hurricane Irma, which, as you know, cost something like for $53 billion in damage. What we looked at actually here is it was reported that in 2 areas, so it was about the same hurricane, Category 3 hurricane in this area here, which includes Lee County and on the one side Sarasota. So what we wanted to know is, given that this hurricane here, the damage which was reported, does that relate to texture, or was this independent of it? So what we did then here is we took Lee County here and built this pair distribution function by taking each building, calculating what is my average distance, making the circles around it, and determine the pair distribution function. What thus turns out here in this plot is that Lee County has a very ordered structure of buildings. In contrast to Sarasota, actually, which has a much disordered structure, which is shown here in green here, with distance being roughly the same. So the question then raised is, if we now run simulations, so computational fluid dynamic simulations running through the city, is the pressure on the buildings affected by this texture effect of these 2 cities? Well, it is. So what I show you here is this pair distribution function on the one side, and on the right-hand side, the average drag coefficient. The drag coefficient plays a role in the sense that the wind load, which one would need to consider, scales with well, the velocity, which in both cases here was the same, but this here is, let's say, a texture parameter which translates texture of the city into a wind load. So it's called the drag coefficient. And what you then see here for a city here, so Lee County, particularly here was Fort Myers, Cape Coral, and Bonita Springs. Similar building heights were considered here. We had about 8,000 to 32,000 buildings to build this G of R. We considered the same wind speed, so 110 megapascals, a hurricane 2 to 3, roughly. But to determine here the drag coefficient over the height. And what you see there is a statistically significant difference between Sarasota County in terms of this drag coefficient, which ultimately will translate into wind load, compared to the one of Lee County. So clearly, geometrical layouts in Sarasota County offer lower drag coefficient for buildings than in Lee County, which results in lower wind loads. So that may have contributed actually to the damage which was reported higher in Lee County than in Sarasota County. So just to remind you how this approach actually goes, it's not that difficult actually, it just needs some good students, which we have here, obviously. You take basically GIS data with heights of a system. You develop an urban model, basically extracting this enriched geometry of the system here. You run CFD computational fluid dynamic simulations in order to obtain the wind loads, and you can then use this in structural analysis. And I come back to this here. And then you look here at verification. You can verify this here with hurricane damage data and look at local city texture characteristics of damaged buildings, eventually to map the risk map for buildings of a city. So let me bring it down to the lower scale. I started at the city scale. Now I was sort of at the scale of the pressure on a building. How do now buildings react to it? And let me first define what we mean by resilience. Resilience is often misunderstood as actually robustness of a system. But in fact, resilience of a city is rather the time it takes, its recovery times, and the rapidity it takes in order to bring a system after a drop in performance back to the same performance or higher performance. So the key quantity is this here. Just imagine if you have a structure completely destructed, the performance will all go down and it may never be rebuilt. So that's clearly not a resilient system. So from a point of view of economic development, from the health, from the community, healthy communities, everything depends on how fast after such an extreme event, which entails a drop of performance, are you able to recover the performance here, determine recovery time, and actually make then decisions at the scale of the building. How can you enhance the resilience here, looking at damage inventories and bring that together with trades in order to evaluate the time it takes for recovery. Just to make the case, classical approaches are based often on the ultimate limit state, meaning for the failure load. But if you look, for instance, at the Hurricane Maria, Puerto Rico, and we all feel still very strongly with the lack of progress in Puerto Rico after the hurricane, which clearly shows there are some issues here associated with resilience, with this recovery time here. If you look here at the map here where the color coding actually tells you the extent of damage, you see a certain pattern emerging here, which you realize actually may well be related here to the city texture. But if you look close into at the building scale, you actually realize that the structure is still okay. What is no more okay is the non-structural elements like the windows here are blown out, so there's no way that people can immediately move into there. So what we need to evaluate in order to come to the recovery time is not only the structural failure, which is covered by design codes, but also the non-structural, the partial or full failure of these systems. Now, how do we do this here? It's not the classical way how engineers do this. Let me use, again, a molecular structure and take away maybe this perception that molecular structures and physics is so complicated. In fact, if you look at the structure on the left, you could well convince yourself that this is just a nice three-floor system here. But in fact, what it is a graphene structure, which is the single-layered, most strong material existing on Earth for which someone obtained a Nobel Prize a couple of years ago. So what we do actually is, if you take this analogy here, the way how physicists model this phenomenon is basically just here by interaction between mass points, where they describe interactions. So we apply exactly the same approach for structures, discretizing a structure by mass points and defining the interactions here. Now you may ask, say, how do we do this? Well, I will not explain the equations, but the idea is basically you start here. This is an energy landscape of interactions here. You are around an equilibrium state, and what engineers classically do is linear elastic simulations here, which is this yellow curve. However, as you move out of the equilibrium, you may have, well, some softening behavior or even a fracture of the system here. So we use these same approaches because they are pretty much straightforward to be used in existing simulation tools in order to model buildings here. And just to make my point that this is not just sort of a nerdy idea coming from MIT, I take here a very practical example here. Two beams, wood beams, connected here by a nail plate. There exists a wealth of data actually in the literature which determines sort of moments versus rotation, angle rotations here. If we use a Morse potential, which was originally developed for water, and you calibrate on it, you actually see that this Morse potential used in molecular simulation perfectly works for a wood structure in order to reproduce the energy of the system. So, and then what you can simulate here is just a proof of concept. You have in red some structural elements, also in gray some columns which are structural. But here you have windows or other non-structural elements. And if you run then simulations with a wind flow here, you see that first the non-structural elements go before the structural elements come out. And of course, if I had here another building, you know, it would be hit by the projectile of this building. These calculations are extremely fast, and it can be used thus at city scale. So important here is the distribution here of damage inventory for recovery time, redundancy, and evaluations. And I just put this picture here just because it looked very similar. It's not an attempt to model that particular building here. But more realistic buildings are shown here. So for instance, the commercial type building, the OE type building here, which we simulate with different discretization. The approach consists actually of something which is pretty much straightforward. What you do is you basically say, oh, my equilibrium state should be exactly the same between a classical engineering approach, for instance, by finite elements, FEM, and this molecular structure. And so you calibrate the potentials on this elastic response. And what you can then run are simulations where you impose wind loads and you determine the cumulative distribution function of failure, so-called fragility curves for each building. So here's an example here for this type of structure made out of wood. They both have the same ultimate limit load, so designed for the same ultimate limit load. But if you look at the cumulative failure probability, taking into account structural and non-structural members, you actually realize that that it's not the ultimate limit load which matters here, but actually the particular envelope of failure. In blue here are just the wind speeds, just to make the point about this here is the 2070 Hurricane Maria in Puerto Rico was reported to have a wind speed of 90 to 125 mph with wind gusts 175. So you're somewhere here in this region here. So you see in that case here that the structure here carried out in timber would have a higher probability of failure, which means a likelihood, which you would need to consider if you want to evaluate the resilience now of these buildings in the context, for instance, of Puerto Rico, whereas gust winds, well, may even affect some of the concrete elements. So these type of information are absolutely critical in order to determine damage inventory, or probability of damage inventory on the one side, and on the second side to calculate the time of recovery with all the probability that comes with it. But how do you actually decide, and that's just for my structural mechanics colleague, how do you actually can say when a structure fails? What I show you in this plot is the energy stored in a building, the potential energy and the deflection. So what you see here as the deflection goes up due to wind load, it comes to an irreversible point, and then you see the deflection continues here. What the curve also shows is that free energy, which is the internal capacity of a structure to store outside energy, work, into recoverable energy, reaches a maximum and then exhausts it. While the external work actually in the end is the overall potential energy, meaning we have exhausted the structure's capacity to determine, store outside load work from the outside into the structure. Now, engineers classically use sort of this point here as a, sort of an ultimate limit state, but that's not the point when a structure actually fails. In fact, if you make a refined analysis using fracture mechanics, you actually realize the following, that the critical point when the structure actually fails is not at the peak load, but later on. And that depends on the type of structure. Some structures that fail directly at the limit load means they have not sufficient ductility in order to attain the system. So that's for those interested, there are 2 papers which are out there on, in the open literature, which we are happy to share with you. So how do we go then to city scale? So just to summarize this, it's a true multi-scale approach. Classical engineering would start on the material scale, brings it into structural, non-structural elements using design codes, formula, going to building, eventually to neighborhood or city scale, which is there. But what is truly needed in order to address resilience of city is a reverse engineering of city resilience, meaning starting at the city scale and bringing it all way down here. Given a certain structure, and I'm not thinking that we are rebuilding our cities to get our crystal structures into a more glassy or amorphous form in order to reduce the wind effect, we need to reverse engineer at a local scale the texture of a city into the right choice of structural, non-structural elements and the right materials. With this, let me just conclude. What resilience of cities was the question raised. Clearly, it's work in progress, and I'm here to discuss this with you. It's true multi-scale. It has one aim to be quantitative at city scale. It is based on integrating big data with modeling in order to provide information to those who are concerned by it, be this the city scale or be this the homeowner, to reduce either operational costs or increase the resilience of an individual building here. And there's some need for reverse engineering. With this, I thank you very much for taking time out. Thanks to all my collaborators, my colleague MJ Comey at UC Irvine, Marta Gonzalez, who was at MIT, who is now at UC Berkeley, Thorsten Amick, Professor Van Dam, Jeremy Gregory, who is online, and of course those who make it happen are the students, Jake Sobstill, Konstantinos Keramides, and Talal. And thank you very much. This work has been done for the Concrete Sustainability Hub at MIT with support provided by the Portland Cement Association and the Ready Mix Concrete Association and MIT Energy Initiative. Thank you very much.
Thanks, Franz. I appreciate it. So as we mentioned, please make sure that you use the Q&A box, which is in the upper right. And you can type in questions there, and we'll be reading them off, and then Franz can answer them. So we have a couple that are here. The first one, Franz, is the question is, what's the impact of adding CO2 to wet concrete?
That's a very interesting. Yes, I know there's some technology. So CO2, I think, has there's a positive effect, which actually it can work. It can improve the workability. I have some samples in my lab actually, where I would like to see whether the CO2 would react with at early ages with Portlandite to form or reform limestone or limestone powder at a very small scale. The tests have not been done, so I cannot conclude on this here. But what is known is that CO2 in the right proportions has the potential actually of improving the workability of the system.
Yeah, and there's some technologies that are available to use that also they claim that then you can use less cement as well when you add the CO2 to the concrete. So, all right, another question is, isn't most heating in New England and Cambridge done with heating oil, not gas?
Well, in Cambridge, actually, the data which we had were all from buildings with gas here. So particularly in Cambridge, I think it's well covered by gas, to my knowledge. At least the buildings, the 6,000 buildings for which we had access through a collaboration with our colleagues in the Media Lab, 3 years of data were gas data. So that simplified the evaluation. Having said this, if one knew the amount of oil which is spent, and I would have this per month and bring this together, a similar approach could be applied to oil data. Electricity is a little bit more tricky in the sense of that we use electricity for heating. Electricity is a little bit more tricky because we use electricity for many other applications. While gas, for instance, we always see a baseline of gas which is for cooking, for normal things. What it takes there, actually, in order to isolate the electricity related to heating or cooling, is to look at the time scale where it occurs. The time scale, actually, let's say here of heating in winter, for instance, is related to a day and night, or the heating of the building. So it's in the hour range, while other spikes of energy consumption are on much shorter time scale. So Fourier transformation, for those who know what that is, provide an access, if you had electricity data, would also provide a means of determining the energy consumption. Oil would be also the same thing because that's exclusively used for heating. So it would actually be easier to make this analysis if this oil consumption was known on a monthly basis.
Great. All right, next question. Who's the audience for this information? For the energy model, when you talk to Cambridge, and the resiliency model, when you talk with Lee County? Is it the city planners, and who would deliver this message? Would you start with the insurance companies or others?
So
who's the audience?
I think this is an excellent question. And to put this in context, I think, let me start. There are several audiences for it. One, the first audience of it, which I think are the resilience officer of cities. You may have heard about it, that there many cities have now resilience officer or sustainability managers of cityscape. So our first discussion here is at that scale. There would be natural partners here in implementing some of these solutions. In fact, we applied for together with the city of Cambridge for a fund by Department of Energy, but that was before the last election. So this is a message which clearly works with the Office of Sustainability and Resilience of cities. The point here of a city is to engage here in re-engineering in a process, and that's a continuum process, of rethinking the concept of resilience of their cities. Right now, most resilience plans that exist for cities, it's just a matter of how high will the water level eventually be, and in 30 years, in 40 years, in 50 years, and are our buildings equipped for this purpose. So this is at time scales which may not be relevant for the next storm. So actually here, helping city managers to formulate a vision and a plan to enhance the resilience of their city, meaning by this here, the resilience here as shortening the recovery time to bring the city back to its performance. That's our first customer. The second one is customer, the people with whom we engage. The second one is the structural engineering community, American Society of Civil Engineers of Association, of whom I'm a proud member, to provide new services for engineers to help cities or communities to enhance their resilience. These approaches, as all approaches, need implementation, and implementation needs education. So that's our direct colleagues in industry and practice, which we want to address, for instance, through this webinar as a first contact. When it comes to the insurance industry, that's a little bit more delicate. And the reason for that is that insurance companies have their own financial models for financial models for insurances, whether it's flood insurance or whether this is damage insurance, and they adapt them as they go along. These models are operating in a highly secret. At least so far, we were unable to get any of them to see how much they match with our things, because that's the core of the business of the industry. So here we have the insurance industry. Even though we would love to engage with this, there's here something about academic research which needs to be open there for everybody versus proprietary information of the insurance. That ultimately this research will impact, hopefully, the models used by the insurance industry. That's part of our hopes, yes.
Great. All right. Is there an analogy to be made here with doping of crystals? Very small amounts of dopants can dramatically change behavior of the substrates. Could we accomplish large changes with only a few carefully selected changes?
Yeah, that's this is a great question, and I appreciate for it. Indeed, it's absolutely true. In fact, there's an extremely interesting pattern which emerges when you look at the energy consumption of a city, which is known as Zipf's law, Z-I-P-F. So you hear my German accent in the background. Zipf's law. Zipf's law actually is is a well-known phenomenon for instance, internet traffic or income distribution. That a few have a lot of income and many have a very poor income, and that's exactly the type of distribution which we obtain when we look at Cambridge, the distribution of the R values or the in Cambridge, right? So this is shown here in this upper right graph here, where or here this energy here, where you rank the buildings in terms of their energy consumption, and you realize actually that if you do a retrofit to just a few buildings, you can largely decrease the energy consumption at city scale. That's, by the way, a phenomenon which is not only true for buildings, it's also true for pavement, for networks. Whether there is a bigger physics behind it, as the question comes to, doping of substrates, we haven't found it yet, but it's a very intriguing question, yes.
Okay, next one. Are there other additives which can be added to concrete to improve the resiliency of structures, such as carbon fibers, steel fibers, etc.?
Okay, so there is already, if it's for concrete structures, reinforced concrete structures are well developed and have a wealth of ductility if they are correctly made. So craftsmanship is still a very important issue to make good concrete structures. Of course, you can make them stronger by adding fibers. For instance, ultra-high performance concrete are based using fibers, sometimes even of different size, in order to enhance not only the strength but also the ductility, which is a huge issue to reduce the potential damage of a structure and thus reduce the time for recovery. But let me use this occasion to say that I think enhancing the resilience at a material scale is the best thought about if you use additives which add at least another function to the material. By which I mean, concrete is not only there for strength. Concrete is there because there's a certain thermal mass. Concrete is there to have protection focuses that doesn't let water come through. So it has more than one function. But particularly if you use an additive, the question which I would always like to ask first, in order to see whether this will have an impact, is what new function would it add to it? So, for instance, there are some ongoing research in the CSH Hub which looks at electron conducting concretes here. So basically, you can create with your concrete wall a battery or something which comes out of it, right? So then you add sustainability, actually, in the sense of that you could use the photovoltaic cells to store the energy not in a heat bath or in the grid, but you can store it in the wall system. So this is sort of the idea. I think when you think about resilience at a material scale, sustainability at a material scale, strength is one aspect, durability is another one, but a third one, which concrete actually is extremely good in, is to add new functions about it. And I think that's much of the discussions which we have currently with the industry in the CSH Hub to add this as one part of our portfolio to our interaction with the industry, the cement and concrete industry in the United States.
Okay, I think just one more. Are the city maps that you have generated available online or in other sources?
So we haven't generated them, we just take them. So there are different ways of doing that here, and we will make them available. So the 2D city maps are available for everybody. You just go online and look for city maps. You can get the coordinates of building and can do this analysis yourself. In fact, I start doing this in classes. You know, I just give a city and redo this analysis. It's a very fast run. We will make the algorithms available. It's MATLAB algorithms and so on. Now, where is it more difficult is to obtain the height. And it's a definition, that's a quantity which is less available for buildings. So we only have it for a selective number of buildings. The good thing about it is that the height doesn't vary so much in a city because of specification, height specification in certain areas. So it is not such a huge impact, but the XY coordinates of a city are all available.
Great. All right. Well, that brings us right up to the end of the hour, so perfect timing. Thanks so much, everyone, for joining us. In case you missed it or you want to share it, we will have a posting of this on YouTube in a day or two. So thanks so much for joining, and we hope that you join us again in a future webinar. Thanks so much. Bye-bye.